Tale of Two Involutes. Where does the tale start? Well, I wanted to see if the involute of an evolute was the original curve. That's what I was trying to find out. So in order to see that, we need to see what an evolute is. Then we need to see what an involute is. And then we need to take the involute of an evolute. And I used an ellipse for my experiments. Now, an evolute is a unique curve that has transparent geometric interpretations, and I've done that several times in the past, so I was familiar with evolute. I had not done much with an involute. That's a different story. I had to find out what the involute of an ellipse was just to practice what an involute was. Fortunately, an involute also has a geometric and an analytic interpretation. I'll show you that. It turns out that a curve has many involutes, and these form a family of parallel curves. So take a look at what it means to have a family of parallel curves. So then I'm finally ready to find the involute of the evolute of the ellipse. And that's what I really started to look at when I began this study. And if the two terms evolute and involute have been wisely chosen by the math community, then it should be that the involute of the evolute gets you back to the original ellipse. The extent to which that happens is what I'm exploring in this webinar. Let's start with some definitions so that these words, involute, evolute, etc., are well defined. Evolute. You have a plane curve R. That's its position vector description. The evolute has a formula R plus Rn, where little r is the radius of curvature and n is the principal normal. Involute. R minus st, where s is arc length and t is a tangent vector. Parallel curve. R plus dn. N is the principal normal. D is a real number. Now, some geometric insight. Evolute. Two different ways of defining or describing or obtaining the evolute. Locus of the centers of curvature, or the envelope of a family of normals. Involute. Curve traced by the end of a string unwound tautly from the curve. Parallel curve. Curve everywhere equidistant from R. So we want to show what these descriptions amount to and how to do the computations. And as we hinted, the plane curve has many parallel curves. It has a unique evolute, many involutes. And these involutes of the evolute form a family of parallel curves, one of which is the original curve. That's what this exploration gets to. Let's begin by looking at the evolute of an ellipse. Two different ways to describe the evolute: via the center of curvature and as an envelope of normals. Here's a picture. This green curve is piece of the ellipse. Right, here's our ellipse going to go this way. Center. Position vector r to a point on the ellipse. At that point, we construct a principal normal, points in towards the center of curvature, but we scale the length of that principal normal, which is a unit vector, by the radius of curvature. So that means that this gold vector is going to go right to the center of curvature. And vector addition, r plus rn, the blue vector, will trace out the center of curvature, the trajectory that the center of curvature makes as it moves along. So what is this locus of the centers of curvature? What will that look like for our ellipse? Okay, so in red we have an ellipse. Green circle is a circle of curvature. Blue dot is the point of contact at which you construct the circle of curvature. Now this black curve is traced by that center of curvature. The gold dot is the center of curvature, and the slider moves the point of contact. The radius vector is going up to that point of contact. So the slider moves that point P, the blue point, as the circle of curvature traverses the ellipse. Its center, the gold dot, is tracing the evolute. So that black curve is the evolute of this ellipse. So let's see if we can obtain that same trajectory as the envelope of normals. Let's see what that looks like. So this is an animation. Here's a slider. It controls the position of this normal line. Okay, and I'm really going to be just looking in this fourth quadrant, points on the fourth quadrant from which a normal line is drawn. That green line is tangent to the evolute that we drew before. If you take the envelope of this family of normals, you get the evolute. Now, what does it mean to take the envelope of the family? The envelope is a curve for which each point shares one member of the family. So each point on the evolute has a tangent which is a member of this family of normal lines. Okay, so you do get the same ellipse from that notion of envelope of the family of normals, and we'll calculate that. So let's do the relevant calculations. We'll calculate the evolute as the locus of centers of curvature, and then we'll obtain the evolute as the envelope of normal. So first, the evolute is the locus of the centers of curvature. And here are the calculations. Essentially embedded them so that you wouldn't have to watch me do a bunch of typing. I've loaded the student vector calculus package. And I like to have vectors displayed as column vectors. So this command tells Maple to display vectors as column vectors, not as sums of basis vectors. I want to define my ellipse, define it as a free vector. So here's the assignment: 2 cos t sine t. In the vector calculus package, there is a principal normal command. If you include the argument normalize, you get a unit vector, and by telling it to treat terms as real, you get a slight simplification. We do the same thing. There's a radius of curvature command, so I just make use of that. I'm going to draw the graph of R in the Evolute using the space curve command in the student vector calculus package. Now, there is a space curve command that has no capital letters in the plots package. Problem with that command that I see is it only works for a curve in space, 3 components. If you want to graph a curve defined vectorially in 2 components, you have to use a different command. You have to use a different approach. This space curve command in the student vector calculus package takes a vector with 2 components or 3 components. It doesn't make any difference. And it draws the curve. So the curve is R plus Rn. That's our center of curvature description. Here is R. That's the ellipse. I put it together, and you see the ellipse here in red and the evolute in black. Computationally, if I take R plus Rn and tell Maple, okay, simplify that. This is what it looks like. 3/2 cos cubed minus 3 sine cubed. And we'll see this again because we want to compute this a different way and show it's the same. So now let's compute the same evolute as an envelope of the family of normals. I want points on the ellipse to be referenced as UV because I want to keep the coordinates x, y for points along the normal line. So u of t is 2 cos t, v is sine t, and I make these functions using the context panel here. A sine function. That's how I did it. Since the curve is now given parametrically with u and v, slope along the ellipse is v prime over u prime. And again, I use the context panel here. I pick a sign. I have to put this here, and you'll see it. Assign name, so that sets m to this ratio. Normal line. Okay, so I use point slope. The slope is the negative reciprocal of m. There's your slope. X minus the x coordinate of a point on the ellipse plus a y coordinate of that point on the ellipse. Y equals, but I brought everything to the left side, so I have an expression that I can make into a function. And assign. Now, how do you get the envelope of this family of normal lines? You simultaneously solve these 2 equations. F equals 0. The derivative of f with respect to the parameter, and the parameter is t, equals 0. So, here are the 2 equations. F equals 0, and the derivative with respect to t equals 0. You solve for x and y. I hit it with a simplify to clean things up. And then by evaluating the names X and Y with the results of this solve command, I get a vector representation of the solution. And if you have a very good memory, it's the same as we saw above. 3/2 cos cubed minus 3 sine cubed. I can in fact get them on the same screen. So here we did it with the locus of centers of curvature, and here we do it as the envelope family of normals. And this animate command animates the drawing of those normal lines, and you see that they are tangent to the evolute found by the locus of centers of curvature method. Okay, by way of practice and understanding what an involute is, let's get the involute of this ellipse. Some pictures help. The red curve is the ellipse. This brownish color curve is an involute. Now, how does that string business give us the involute? Okay, ellipse. The black portion represents a string which has been fastened here at point F. Point P is where I will put a pencil so that as I unwind the string, the pencil will trace a trajectory. And here is an animation that shows that unwinding taking place. Now, you see two green arcs, two green things. One is on the ellipse and the other one's a straight line. As you unwind the string, you are uncovering a portion of arc length, S. That's equal to the length of the string that's now off the ellipse. So these two green things have the same length. You can see here at the bottom the piece of this curve, the involute, being traced. So I'll do this frame by frame so you can see that happen slowly. You're pulling on the string, it's taut, the string leaves the ellipse tangentially because of the tautness. And now I'll just wiggle this thing back and forth a couple of times. And you see a portion of the involute being traced by this taut string definition. R minus ST describes this involute analytically. In the next figure, figure 4, we're going to examine more carefully how this string process relates to the analytic description. So let's take a look more carefully at this figure 4. Point M is the point at which the string leaves the ellipse. Arc length S, radius vector to that point M. T is a tangent, unit tangent vector in the direction of traverse because the ellipse is drawn counterclockwise according to the parametrization. So if the arc length is positive and strictly increasing, then minus st will point not this direction where the goal vector t is drawn, but minus st will point in the opposite direction, and it will point down here to point P, the tracing point for the involute. That's why R minus st. R, not plus, but plus the negative st points down here. Let's look at the calculations by which this involute would be found analytically. We're going to need that gold tangent vector, so we use the tangent vector command in this vector calculus package. Comes out to be this unit vector. We want arc length, so we need an element of arc length. And what's the element of arc length for a parametrically described curve? It's x prime squared plus y prime squared square root. Well, there's a differential at the end, but Maple's integrals don't explicitly have you enter the differential. So element arc length, EAL, element arc length. What is this square root? It is the length of the derivative of r, and that turns out to be this square root. Now I want to integrate that. I want to integrate it from 0 to some stopping point, called the stopping point A. Well, Maple's int command doesn't know if A is greater than 0, less than 0, equals 0, how is it related to t. So I've put in the all solutions so that I get a piecewise solution containing what happens if A is greater than 0, less than 0, or equal to 0. So then I do a simplification on that expression with the assumption that A is greater than 0, and branches of that piecewise function go away. And then I want the expression for the arc length to be a function of t, not a function of A, so I replace A with the letter t. Now, because of the cusps, you've got pi over 2, pi, 3 pi over 2, and 2 pi. Things behave strangely at those points. So I simplify this arc length expression, assuming that t is between 0 and pi, and then I simplify it assuming that t is between pi and 2 pi, and you can see the change in the expressions that you get. You get elliptic functions for sure, because arc length of an ellipse is given in terms of elliptic functions. That's where the name elliptic function comes from. This down here is the floor operator, and so Maple is looking at how many pi's there are in this mix, in this menu. I graphed this expression that I got for S. It is monotone increasing. When I use it in R minus ST, right? R, we know what R, we defined R. T is this tangent vector up here. Okay. S is this expression that I got here. When I use it, I get this spirally looking thing, which is the involute. It looks like it should be right. Family of involutes. If I replace S with A plus S, for each value of this parameter A, I'm starting the curve at a different point. I've tried A with these three values, minus 1, 0, 1. And you can see this is 0, this red one here. And then these two indicate that I've changed the arc length to start with. And here is this family of involutes. So now we're ready to consider the involute of the evolute, because we now know how to do involutes. But before I did that, I asked myself, could you even recover R from its evolute? Because this investigation is to see if you can recover R from the involute of the evolute. Just can you get R from the evolute? So here's what I tried. Here is the ellipse. This is the evolute. Can you, knowing the expression for E, that's this vector, reconstruct from this formula what R was? Now, R is R, but there is an R hiding in the principal normal and in the radius of curvature. So really what you have is on the right-hand side these derivatives. And you want to set these derivatives equal to this vector to see if you can solve the resulting differential equations to get back what x and y are. Well, I use as initial conditions the ones that correspond to the ellipse. So a little bit of cheating there going on. I just want to see if this would work. So you get two differential equations, one for each component. Here's one, here's the other. Toss them in desolve along with these initial conditions, and I did get back 2 cos t sine t. I did get back R. So that was kind of a nice step along the way to say, okay, you can recover R from its evolute. But what we're trying to do is to recover R as the involute of the evolute. Let's see if we can do that. Let's compute, finally, the involute of the evolute. This is the evolute. We need a vector tangent to the evolute. So we use the tangent vector command. We apply it to this curve, normalized, and we do some simplifying because of those nodes, and we have these absolute values, and you need the absolute values. It turns out you really need these absolute values. We need an element of arc length along this evolute. So we use the same idea that we used earlier. Take derivative square, square root, which is really just take the norm of the derivative. So I differentiate, take the norm, and need to do a little simplifying again because of the nodes. So we get this expression, and it has absolute values in it. And again, the signs will matter. So that's the element of arc length, and we have to integrate that. And so I did what I did earlier. I integrated from 0 to a, and I tried that, and a whole lot of other things. And I got funny curves that resulted. Things just did not work until I tried this. I got the indefinite integral of this expression. And you can see here signum, sign of, because the signs matter. I graphed this expression for the arc length. It's discontinuous. And from some points of view, you can say it's monotone if you wrap plus infinity around to minus infinity, or it's not monotone if you consider this drop from positive to negative. And I looked at this and I said, what's going on here? Does this thing even work? If I simplify E minus st using this expression for the arc length, lo and behold, it's 2 cos t sine t. It's the ellipse. And here I've done simplifying between 0 and pi, and here I went from pi to 2 pi. This works. Why? Why does this work? So let's draw some pictures. This animation reminds us of how the ellipse and its evolute are drawn. Okay, as this top half, this first quadrant portion of the ellipse is drawn, this fourth quadrant portion of the evolute is drawn. Second quadrant here, third quadrant here. And you can see the direction in which the tracing is done. Now let's look over here at this animation. Here I'll use the slider. Red vector is a position vector to a point on the evolute. The evolute is drawn downwards. So this black vector is a tangent vector in the direction of motion. The green vector is the negative of the arc length times this black vector. So it points in the opposite direction, because here the arc length is positive. Consequently, you get this gold vector, which puts you on the ellipse. But what happens if you go a little bit further? Let's go to this branch of the evolute. The black vector is tangent in the direction in which the evolute is traced. But here, if the arc length were positive, minus st would point in the opposite direction, would point this way. But it needs to point this way in the direction of this green vector to get up here to the ellipse. And so that's why the negative arc length works in this quadrant. And it was finally that picture that enabled me to get past this spot, because that negativity of the arc length working drove me absolutely crazy. Family of involutes, curves parallel to R. Begin by making sure we understand curves parallel to R. Parallel curves, R plus dn. Right? So you're taking the principal normal and you are scaling it by d. If d is positive, the curve will be inside. If d is negative, it will point the opposite way, and the curve will be outside. Here is a slider. You can see d is in this negative range. You can see you get a family of curves that are oval and are outside the ellipse. That's the family of parallel curves, or curves parallel to R. Well, one of the things that struck me was, are these parallel curves themselves ellipses? It was not easy to answer that question. So I said, okay, if this is an ellipse, this is the semi-major axis, this is the semi-minor axis. Those numbers are given by these two vectors. This would be the x coordinate out here, 2 minus d, and 1 minus d would be the length of this segment. Then the components of the parallel curve, if they're going to be an ellipse, you would have the x component divided by 2 minus d, the y component divided by 1 minus d, each one of these squared, added. If it's an ellipse, this adds up to 1. So basically, I ended up examining lambda graphically because lambda is a very messy expression. So I graphed this expression, lambda, and this is lambda equals 1. And you can see there is just a single value of d for which lambda is 1, and that's d equals 0. So these are not ellipses. These parallel curves are not ellipses. So let's get this family of involutes. The way we'll do that is add to the arc length. But notice it says signum. So in other words, when arc length is positive, you want to add a positive amount. And when the arc length is negative, you want A to be negative. So that's what the signum will do here. And the slider shows what happens to this family of involutes of the evolute. Right? This is the E is for the evolute, and this is the family of the involutes of the evolute. It appears to be the same as this family. Can we get some analytic proof that these two families are the same? So we have these two families of curves that might be parallel curves for the ellipse. Now, this was directly computed as a family of parallel curves for the ellipse, so we know that that's okay. Then we have the family involute or the evolute. They look the same. Can we get analytic evidence that they are the same? So here's what I looked at. I evaluated each family at pi over 4 to get some insight. This one has D as the parameter, and this one has A as the parameter. And I noticed that if D were minus A, these two families would be the same. So I said, okay, let's set A equal to minus D and compare one family to the other by see if the simplification goes to 0. Well, you have to avoid those nodes. And here, between 0 and pi, it works. Between pi and 3 pi over 2, they're the same. Between 3 pi over 2 and 2 pi, they are the same. So there's two families. One parallel curves that we got around the ellipse directly, and the family that we got as involutes of the evolute, they're the same. So by way of finishing here, let's remind ourselves, Tale of Two Involutes. What are the two involutes? First involute we looked at was the involute of the ellipse, just to get practice what an involute was. The second involute was the involute, the evolute. That's the second one. And the final thing here, I think I will give you my email address, rlopez If I can type that at maplesoft.com. If you want to copy this worksheet, send me an email, ask for the worksheet, and I think I can just attach it and send it back. This should go through without needing a download. Thanks for attending.